Okay, we're live. Um, hey everyone, I'm Shrikar, the Vice President of Enigma, the Computer Science Club of Mahindra University, and welcome to our first ever live stream. Along with me, I have Anshit, who's a 2017 batch computer science student and is a game developer and works on Unity. And I also have Ronak, who's a 2020 batch student and he has worked with me on this project. So, yeah, let's get into it. Maps in video games, you probably wouldn't have paid much attention to them, or you admired the beautiful terrains of Minecraft and the bright and colorful lands of Genshin Impact, or never cared in times uh, where you have to clutch in CSGO. So, with that said, um, I would hand over to Ronak, who would discuss a bit on map generation.
Yeah, so have you ever wondered how maps are actually generated in games? Well, one of the process or one of the most common process is basically you have a panel of game devs or game developers and who actually design all these maps. So they are like pre-designed. Okay, so whenever players move forward or goes through the game or progresses through the game, basically, they know what's going to come. So you know the map already. So it happens in like CS:GO or Counter Strike and then IGI maybe. But there are few games which require like automatic generation of maps, like Minecraft. Even the game devs do not know what's going to come in front of them. They follow a set of rules and they generate maps on basis of that. So that's very cool actually how the game generates the maps for us. So we came across this popular idea called cellular automation, which is a very fancy term, I agree. It's basically Conway's game of life, and we are going to actually explain what Conway's game of life in a bit. So, why are we even talking about this map generation in the first place? Well, let's hear it out from Anchit himself.
Hi, I'm Anchit. I'm from the 2017 CS batch. I've been making games for quite a long time now. I usually use Unity, which is a really cool game engine. So talking about map generation or procedural generation, why is it relevant? The thing is, with like traditional way of making games, what you would do is you would place every single object or item or the map itself, the enemies and the players manually inside the game, which is obviously a lot of like time or and resources that are being used for creating the levels and environments. Instead of that, why not use procedural generation, which can create all your maps for you? So the thing is, it like these days, AAA games take hundreds of millions of dollars to be created. So procedural generation is a good alternative to quickly create a lot of replayability, and at the same time, decreasing the amount of money and time and resources you're spending on your game. So I just want to share a few clips about this. Let me share my screen. Give me one sec. And should be visible. Can you guys see my screen? Shrikar, if you can give me a go ahead. Okay, cool. So a small thing I just wanted to show. So this is called Perlin noise actually, and it's just a texture with like a black and white texture which is randomly created, and you can easily use this to create a terrain. So that value between a 1 and 0 for black and white would be just as a height, and you can very easily create a simple terrain with this. That's it. A simple way to create a terrain. I'm really sorry if you can hear my cat in the background. She's being a little dramatic today. Anyway, next clip. Next clip is from Dead Cells. It's a procedurally generated roguelite game, which uses procedural generation. It the creators of Dead Cells kind of use an interesting way to generate the levels. What they've done is instead of like handing over everything to the computer, the level designers create, like manually create small chunks, and they create tons of these small chunks or levels, and then they hand it over to the computer to like put it together, and that's how they create all the levels. So it'll still, for the player, it'll still seem like every time you play the game, it's a new level, but it's an easy way to still so that it's a different thing every single time. Next up, it is similar to Dead Cells, and the game is called Binding of Isaac, but this is top down. So again, what they do is every level is a small box with like 4 entrances on all the 4 sides, and then the computer will go in and randomly put together and create your level for you, and then it'll randomly decide what's the start box and what's the end box, and just have and you just have a level at the end. Okay, before I show you the next clip, I've actually created a simple level, like a procedural generation algorithm on Unity. So just to explain you the basics of it, so there are 3 things here. This is a floor, if you can see the screen, and this is a wall tile. All of these are like 1 units, and this color is the just an empty cell. So how it works is, 1 second, yeah. So what it does is it places these floors first. How the algorithm actually works is that I'm calling this term a walker, and what you do is you first place an X amount of walkers in the scene. I've used 30 here, and every single loop, the walker will randomly change its direction, or it'll choose to die. So what you have is like over like 100 loops or 200 loops. Have these walkers kind of roam around the entire scene, placing all these floor tiles, and you will have your basic map. And then what you'll do is you'll go back to it again and place all these black colored wall tiles. That's what it's doing right now. Give it a second. It'll complete. So yeah, it'll place all the floors and all the walls, and then again it'll go and remove all the single walls because it kind of looks a bit ugly. So this is what it does every single time. There are a few more like factors here, like you have to decide the actual size of the map. All of these factors are like you can decide all these variables. Let me just show that. Yeah, so this is a chance for the walker to change its direction, or a like chance for a random walker to like be placed, or a chance for the walker to destroy itself, and the maximum number of walkers, and the percentage of the map to that you want to fill. And yeah, exactly like the other ones, you will have a different level every single time. So going back to the last clip, I was kind of inspired by this game Nuclear Throne to create this generation. They've used a very similar approach to create their levels. Just take a look, and this thing uses the approach that I was kind of inspired by them, basically. And that should be it. I'm done. I'm handing it back over to Shrika.
Yep, that was very informative. Thank you, Anchit. So now, yeah, let's talk about Conway's game of life. So, which Ronak kind of brought it up previously. So, let us assume we have a huge grid filled with cells, all right? And each of these cells have only 2 states, either dead or alive, which is on or off. So, as you can see the grid here, we have some cells which are blackened out and some which aren't. Majority of them which aren't. So the black ones can be taken as the dead cells, and the white ones can be taken as the alive cells. I'm sorry, the other way around. The black ones can be taken as the alive cells, and the white ones can be taken as the dead cells. With that said, uh, Conway's game of life is established on 4 rules, right? And these 4 rules are as shown. The first rule, they are simple 4 rules. The first rule is any cell that with fewer than 2 neighbors dies analogous to underpopulation. Any live cell with 3 or more, or 2 or more two or three live neighbors lives on to the next generation. Any live cell with three live neighbors dies as to overpopulation, and any dead cell having exactly three live neighbors becomes a live cell similar to reproduction. So you can see the images which portray the same. The blue colored cell is the live cell of focus, and we can see what happens as it passes on from one generation to another when these rules are applied. So now, when these four rules are applied on a large scale with a lot of cells, we get some pretty interesting patterns and designs. Yeah, these were some of the outputs that we have got from running Conway's Game of Life for for certain generations. So these two GIFs that you can see are two separate simulations of the game of life. So now let's have another small discussion on the map generation again for a bit. So as we've discussed, automatic way of generating maps, which is used in Minecraft as we keep moving, or in Terraria, which we probably know of. And we have pre-designed maps that are pretty much constant throughout the game, as in GTA or Genshin or CSGO. So now Ronak will explain how we related Conway's Game of Life to map generation, how we generated maps using it. Ronak?
Yeah, so we have already seen what simulations are in Conway's Game of Life. So what we have done is we have ran 100 different independent simulations of Conway's Game of Life. It's similar to the one that you have already seen previously. And for each simulation, we ran it for like 100 generations. That means it's simply take it as like we have applied the rules of Conway's Game of Life 100 times in each simulation. And whatever output we are getting, so we get 100 different outputs and then we add them up. So what I mean by adding them up is basically matrix addition, which you probably know of. It's basically you have two matrices and then you add them up where each integer, okay, so each integer represents the altitude at that point. So yeah, so one means like you can say it as 1 meter height, four is like 4 meter height, something like that. So basically, what the integers represents is altitude. So higher the number over there would represent mountain and peaks, and the lower number, yeah, it would represent valleys and trenches. So after applying all this, we get pretty cool outputs. As you can see, let's have a simulation over here and you see how they are actually generated. So we are adding all the simulations together and this is how we are generating the maps. It is pretty cool actually. But over here, you can see a problem. There are so many peaks, there are so many mountains over here. So it's kind of difficult for the player to go forward. So why don't we just smoothen them a bit? Like instead of having so many let's just smoothen them. And we have already a concept in mathematics called Gaussian smoothing, which we have actually used in this. And then we come up with pretty cool outputs, as you can already see in the screen. So yeah, so the one in the left hand side actually becomes the one that you see on the right hand side after applying Gaussian smoothing. So let's just apply Gaussian smoothing a bit more and see what happens. So now you see when we apply Gaussian smoothing a bit more. So this somehow somewhat looks like a map in Minecraft, which is pretty cool. And if we lessen the smoothing a bit, then we end up with something which is shown on the left hand side. So now let's Rika demonstrate the generation of the map. Over to you, Srika.
Yep. So here um, we have two independent random simulations of the map. And yeah, so the map which we made is not just an image, and it's an actual interactable object which we plotted using matplotlib. So yeah, here you can see that as I rotate the map, we can see different angles and a lot of peaks and trenches. Uh, this is another generation of the map with the same method, but the degree of randomness is so high that we would probably never get the same two terrains. And yep, with that said, uh, you could probably run the same code on your computer. We have hosted the code on GitHub. It's open source. That means you can just go take the code from there and run it on your computer and you know use it. It looks pretty cool, right? So you can use it as your background images or anywhere you please to. And yeah, if you find any more cool terrains, you could shoot us up on Discord with those images. So these were some of the resources we referred to during the project. And yeah, you will find all these links in the description as well. So yep, that's it for today. Uh, Thanks for tuning in. See you next time.